All right, let's go ahead and take a look at this one. A 0.98 kilogram block. Oops, I'm still on the highlighter from last one. M equals 0.98 kilogram block slides on a frictionless horizontal surface with a speed of 1.3, so we'll call that V initial, 1.32 meters per second. So we've got a frictionless surface and we have a block, mass M, sliding with speed VI, and it encounters an unstretched spring. So we have a spring here. Okay, and the spring's attached to some wall over here. With a force constant K, which we'll say K is 245 newtons per meter. And then it's going to hit it, and how far is the stretch string going to compress before it comes to rest? So with this one, we can actually do this with energy here. We can look at this and say that the energy stored in the spring when it is fully compressed has to be the same amount of energy that the block has as it's sliding along there. So we can say potential, or we can say is mechanical energy initial equals mechanical energy final, which means over here it's potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Now if we look at this initially before the spring is compressed at all, there is zero potential energy. Afterwards, after it's fully compressed, the block has come to rest, nothing is moving, and there's no kinetic energy at the end. So essentially what we have here is purely the block's kinetic energy, and it has to equal the potential energy of the compressed spring, 1/2 kx squared is what it has to be there. And so that's what we're going to look for here when we do this. We know V, we know M, so if we're looking at this, we know V, we know M, and we know K. So the only thing we have to find there is X. So the 1/2 will cancel out, and we'll get X equals square root of mvi squared over K, just like that. And so then we can go ahead and just solve for that for when it does this. So we get square root of m, which is 0.98 kilograms times 1.32 meters per second, and that whole thing is squared, all divided by 245 newtons per meter. All right, if we go ahead and do that, we see that our newton per meter, the meters will cancel out, so that newton per meter in the bottom is a kilogram per second squared. We have a second squared. We have a kilogram per second squared in the numerator there inside the square root. So that'll cancel out, and then we'll be left with just that meter squared, and then we can get rid of that there. So under the square root. And so if we go through and we do this, we've got 0.98 times 1.32, and the 1.32 has to be squared, divided by 245, and then take the square root of that, and I get 0.08. Of course, be sure to check me on that. 0.0834484 meters right there. So about 8.3 centimeters right there. So it won't stretch it, that's not too much, but anyway, we have that there. So that would be our answer to part A. It would take it that long before it came to a stop. Now, if we look at Hooke's law, we can say for part B, we have F equals negative K times X. We have K, right? And the force, though, is going to change as it approaches, as we go through this. So we can't just say, oh, well, MA equals negative KX, and then we say, oh, we know X, we know K, let's find A and then go through and just calculate it, because that's not really going to work for us, because that acceleration isn't a constant acceleration. So instead, let's take a look at these here, right? Remember these things? So remember here that maybe we can go through and kind of use some of these. So we know the amplitude here